Hi everyone. Today we're going to be tackling the beginning of a new chapter, that being concurrency. Now it's a fairly long chapter with lots of different things, but to kick it off we'll be looking at threads. Now threads could be summarized to basically mean dividing up a single process into multiple processes. So we're going to be looking into a lot of things that will carry over from multi-processing and stuff like that, which you've already tackled. So this should be easy to pick up and understand. But before that, as usual, just a quick recap of last week. We looked at scheduling, which was the arranging of different processes in an order at which best suits our needs and processing those processes in that order. So whether it was optimizing for performance or fairness or a bit of both. And while learning about that, we looked at some basic schemes of scheduling, like our FIFO as usual, shortest job first, stuff like that. We learned about a few metrics, which I alluded to there with the performance metrics, like turnaround time, as well as some fairness metrics as well. And then afterwards we tackled some more complicated or more advanced scheduling strategies. The first being a multi-level feedback queue, or MLFQ. And lastly, there's also proportional share strategies like the lottery method as well. So that was last week, but like I said, for this week we're looking at concurrency. Now in the real world, obviously different activities all happen at the same time or proceed at the same time. For example, members of band, well, all the members of the band might be playing instruments or singing, and they're all reacting to each other's pacing, as well as the crowd probably as well. And the same can be said for cars driving on a road. While you're driving, you're constantly observing the environment and reacting to other cars. Well, hopefully at least. So in the real world, concurrency is everywhere. The real world is concurrent. And we use this word concurrency to refer to multiple activities at the same time. Now, just like the real world is concurrent, so are modern computer systems. And some examples of, well, example applications of concurrency in computer systems is, well, network services, for example. They handle multiple requests from their clients. And you could think, well, this is definitely obvious. Now imagine Google only handling one page request at a time. So if I open up Google and I try to search something, well, I'm put into some extremely long queue, while other pages are being sent out to other users, right? Obviously this is all happening at the same time. Even the application itself, like Google Chrome or Firefox, these applications have multiple user interfaces, where these are essentially multiple programs all running at the same time. And then thirdly, when we're looking at like just parallel programming, this is also an example of concurrency because it's the utilization of multiple processes at the same time. So the question remains, well, how do we achieve this concurrency in computers? Well, in the real world, it's easy because they're separate, like people are completely independent of each other and they're doing different tasks. But in a computer, it's obviously governed by a single operating system. So how do we get this to work? Well, from the programmer's perspective, it is much easier to think sequentially, right? We all do this. We have our functions. They start at the beginning or the top and they work their way down, and it's easy to understand. Now the question is, well, how can we write a correct program which with dozens of events all happening at the same time? So how can we break up our sequential understanding into something that's a bit more parallel? And by correct program, this is important because we still want the program to perform or to calculate solutions or to perform tasks correctly. And that becomes a lot harder when working in parallel, as we'll see later on in this lecture. Now, the key idea is to write a concurrent program, and that is one with many simultaneous activities. And the solution to how we go around or go about doing this is threads. So threads are a set of sequential streams of execution. So ordinarily, you're thinking of a program, we start at the top, it goes down until it returns some value, right? That's sequential. Now, a thread is basically just a set, or threads, sorry. Threads are a set, so just a group of these sequential streams of execution, and they interact and share results in a very precise way. So a thread, you can hypothetically think of it as just multiple processes, but they're not quite like that. And threads let us define a set of tasks that can run concurrently, while the code for each task is sequential. Each thread behaves as if it has its own dedicated processor. So once again, just like each process feels like it has its own dedicated processor, thanks to the illusion of the operating system, each thread has the similar mindset. And utilizing threads often requires additional work from us, from the application programmer, for coordinating. And that goes back to that idea of correctness. Say I figure out a way of dividing up my tasks. How can I then bring it all back together? That requires a little bit of coordination. And we'll see more of examples of why coordination is required as we go along. Okay, so like I said, the operating system provides the illusion that programmers can make as many threads as needed, and each of these threads will be running on its own private or dedicated processor, and this is a virtual form of the processor because the operating system has provided that illusion. And the diagram below is kind of what we get. So in terms of the programmer or the thread's perception of reality, we have something like this on the left-hand side, where we have, say, made up 5 different threads, and each of these threads thinks it's running on its own processor. But in physical reality here, we have, say, only 2 real physical processors. So this is in a multi-processing sense, where there's multiple CPUs. Or more realistically, multiple cores, which allow for multiple jobs to run concurrently. We have this physical reality, right, where there's only 2, and we have still got the same 5 threads, but now what's actually happening is we only have 2 running, so like 1 and 2 here hypothetically, and we have 3 waiting to be run, or they're ready. So again, this should be ringing some bells for you. This is exactly the same as when we have multiple processes, where in our case before we would have like 1 running and all the other ones would be stored in memory, right, waiting. And if they had been processed before, well, their saved states would also be stored. And these concepts are all the same for threads. So in reality, a machine only has a finite number of processors. In this example, we said 2. And it is the job of the operating system to manage and link the running of the threads onto actual hardware. So our operating system maps our threads to specific like processes. So here we can see it's been mapped to 1 and 2 for 1 to 1, 2 to 2, 3 to 1, 4 to 1, and 5 to 2. And that is the job of the operating system to handle this. So we kind of have a sense that threads are very similar to multiple processes, but what is the intuition behind using threads? Well, in a program, we can obviously represent each concurrent task as a thread, and each of these threads provides that abstraction of a sequential execution similar to a traditional program. So just like I was alluding to before, well, traditional programs can be considered as just single-threaded programs, right? A program with 1 thread. As in traditional programs, just each instruction follows the next. Now, a multi-threaded program is a generalization of that same programming model of sequential execution, where each thread or each like sub-program follows the single sequence of steps. So if you have a multi-threaded program, it's basically a program where functions are divided up into threads, and each thread performs a specific function. Now, the benefit to this is that a program, instead of just having one stream of execution from like the start to the finish, now a program can have several or multiple threads executing at the same time. So multiple streams of execution. And just naively thinking, well, you think about doing multiple tasks at the same time, you get this idea that, well, if you're doing multiple tasks at the same time, well, you can finish them quicker. And that is the main draw to having threads, is obviously performance increase. So how do we notice, or how can we think about threads in the real world? Well, I've just taken a screenshot of like a Google Maps image here, and hypothetically I've divided them up into what the threads could be doing. So for example, thread 3 and 6 could be threads that handle the rendering or the actual drawing of the pixels of the top half of the map and the bottom half of the map respectively. Thread 2 hypothetically could be a thread, and a thread once again is just like a function that handles the calculation and rendering of the path, or the shortest path between the 2 points given. Thread 5 could be handling any overlays that you have in terms of like your Google account overlay as well as the Google Options button. Thread 1 could be this left-hand side user interface, where you can obviously input the different destinations and stuff like that. And thread 4 could be handled this bottom button where you press it and then you can see the satellite view. So this program, Google Maps, can obviously be broken up hypothetically into lots of different individual tasks. And that's what is happening behind the scenes. So the 4 reasons to use threads is programming structure, responsiveness, performance in terms of processing, and then performance in terms of input-output. Now we're just going to break these down into a little bit more detail. So our programming structure is important because it allows us to keep track of multiple concurrent tasks. So threads let you express an application's natural concurrency by writing each concurrent task as a separate thread. So many problems that you'll face in terms of programming will have obvious ways in which you can divide it up into multiple tasks, and threads allow us to express that. So one example is, well, to get the screen input while also redrawing the screen pixels requires the physical processes to split their time. One is to get the position of, say, a mouse, or the position of the pixel, and then the other one would be to actually redraw the screen pixel. So naively, once again, you could manually implement a program that would switch between these activities. That's what interleaves means, basically to swap or to switch between. So you could have some interleaving that would look like this, where you would draw some pixels, then you would check for a mouse input, and then you would draw some pixels again. But this is a lot more taxing or tedious for the programmer to do themselves. Instead, they could just utilize threads, which greatly simplifies this process, because now instead of the programmer determining when to swap between these tasks, the operating system just handles it for them. And just like we have a scheduler, which will handle scheduling different processes based on obviously different things like starvation and all those concepts we handled before, well, it applies the same techniques to threads. So you wouldn't even have to worry about this interleaving problem because the operating system would handle it for you. So that is one of the benefits, this programming structure. Another one is responsiveness. Now, in order to preserve responsiveness and performance, a common design pattern is to create threads to perform work in the background. So responsiveness, another example for this would be, well, most of our applications will have like a main loop, right? Which would say, I'm going to execute some command and then wait for another command. Just like you have a program where you need to input data and then it will do something and then you have to input data again. So here in this case, what if some command or some function takes a long time? Well, the user will have to wait for that execution to finish before a new one can be given, right? Ordinarily, in a single-threaded or linear sequence of processing. However, with threads, we can shift those time-consuming commands onto another thread and then continue cycling this main loop. So while that is processing, we can then continue the main loop so that the program is still responsive. So I can perform one calculation and then move on and still, like in terms of the Google Maps, I could say determine the distance between these two or the shortest path between these two, and I could still then be like moving around the map and looking at things if I wanted to, because hypothetically that time-consuming process has been shifted onto another thread, so I can still continue. So that's responsiveness. Performance, obviously, a big one. And in terms of processing, well, there's performance in terms of I/O that we'll look at and performance in terms of processing. So here, programs can use threads on a multi-processing machine to do work in parallel. And if you're doing work in parallel, well, that means you can do the same amount of work in less time. Right? If it takes me 20 seconds to do 5 tasks ordinarily, well, that means it would only take me 4 seconds if I was doing them all at the same time. I think my math works out there. So another example of this is, well, once again, the Google Maps. On Google Maps, a single-threaded machine would have to render each pixel on its own and do this for the entire screen. However, on an 8-processor machine, we can divide that task up into 8 pieces and spread it over the 8 processors. So if you think of like an HD screen, which is 1920 by 1080, that's a lot of pixels to do one at a time. Wouldn't you rather prefer to do it in 8, or that time divided by 8? So this would obviously decrease in 1/8 of the time. That's what I was trying to think of. Thus decreasing the time to take to complete this job, which is obviously better, right? Faster is definitely better. So the last bonus that you get, or advantage that you get with processing in parallel as well as multi-threaded processing specifically, is an I/O performance increase, or an input-output performance increase. Now, computers obviously are constantly interacting with the outside world with input-output devices, right? We're constantly using the mouse to click on things. We're constantly typing on our keyboard, as well as utilizing other input-output devices. Now, by running tasks as separate threads, when one task is waiting for an input-output events to occur, well, then the processor can make progress on another thread. We looked at this last week in terms of just scheduling normal processes, right? Where while one process was waiting for input, we could process another process on the CPU during that time, right? Well, here again, it's the same idea, where if we have one thread that's waiting for an input-output event, well, during that time, we can have all the other threads still being processed. We don't actually have to wait. And we could even leave it in the CPU to just to wait for that input-output, right? We wouldn't even have to swap in another process. Obviously, we do, because that's still even better, though. But the idea is that while one thread was waiting for input-output, because you have all these other threads running at the same time, well, they're not affected by that. So the example I give here is the latency to read from disk can be like 10 milliseconds, for example, which is enough time to execute millions of instructions on modern processors. But with a thread-based program or programs, the processor can quickly switch to another process or thread in that interim time. And that's exactly what we looked at last week. While earlier on in the course, we looked at process abstraction. While processes are very similar to threads, so obviously we're going to have to look at some thread abstraction. Remember back to this diagram here where I demonstrated that for threads, they think they each have their own dedicated processor, but in reality, that's not the case. And this is exactly the same as what processors thought. So our operating system provides the illusion of an infinite number of processors, but the underlying hardware only has a limited number of processors, right? And it is the operating system's job to map these threads to processors. Now, the operating system also uses a thread scheduler, so exactly the same as the scheduler that we looked at last week, or same concept or idea, and it uses this scheduler to switch between different threads. So in terms of the programmer's view, if we had this hypothetical program just doing a couple different maths operations, one possible execution of this could be where it just runs from top to bottom sequentially, right? But however, another possible execution could have been where we do the first line. This thread is then suspended so that other threads can run, after which the thread is then resumed so that the rest of the execution can take place. Now, this is again, it's exactly the same as how processors see things, where you would have one process, say this was like process A, where we have one process A starting here, performing one thing, and then maybe an interrupt occurs. And that process A is then stored or saved, and another process like process B is run, after which process A is then resumed. That idea of like the context switch. So you can see how threads once again are very similar to processors in how they operate. So each thread runs on a dedicated virtual processor, once again, just trying to reiterate that, in terms of its own perception. And that is because, once again, like processors, its state is saved. So wherever it left off, it can be started back up again. The idea here, though, is that because we have these switches behind the scenes that we aren't fully aware of, or the thread isn't aware of definitely, the time it takes to process a thread is unpredictable and variable. It's not constant and it's unpredictable as well, because we have no control of this thread scheduler, right? On the next slide, I'm going to show you a couple different ways in which multiple threads can be executed. And this answers the question, why is the speed unpredictable? And that's simply because threads can be interleaved or swapped or switched in many possible ways during runtime. For example, we could have an execution number 1 here where thread 1 is processed completely, then thread 2, then thread 3. Another possible one is where all 3 are processed at the same time on separate CPUs. Okay. And then execution 3 is where it's a lot of swapping is taking place, where we do 1 a little bit, then 2 a little bit, then 1 again, and we're just breaking them down completely. So here you can see these are all potentially viable executions of, say, these 3 hypothetical threads. And there's no way in which we could have predicted when one was going to start, when one was going to finish, or how long a particular thread was going to run for. None of that information could have been predicted. So with that being said, multi-threaded programs should make no assumptions about the behavior of the thread scheduler. And additionally, execution speed may vary based on normal operations such as accessing disk. So some of these, for example, say thread 1 here, could have performed a like an input-output request. And because of that, the thread scheduler deemed that it should be taken out of being processed or taken off the CPU, and then say thread 3 be loaded, just like last week. So there are lots of different things that will affect the speed of processing of threads. Now the question is, well, obviously the orders here are completely random, it seems, to a certain degree. Now, does this order of execution even matter? Do I care that, say, in execution 1, thread 1 finished first, and then thread 2, and then thread 3, whereas in execution 1, okay, they both finish in the same sequence, but you get what I'm understanding, or you get what I'm trying to say. Now, the idea here is that, well, if threads are completely independent, so they aren't influencing each other, or they don't even communicate or share anything, so they share no memory or other resources, well, then the order of execution does not matter, right? Because I do not, or say thread 1 does not affect thread 2 at all, well, then it wouldn't really matter which one is processed and in what order. However, this is not usually the case. Most multi-threaded programs share data structures, and they communicate between each other. And because of this, the programmer must use some explicit synchronization steps to ensure the program correctness, regardless of the execution order. And that is what we're going to be looking at next week when we tackle locks. So locks is one of these forms of synchronization that allow us to ensure correctness of execution. That brings us to the end of the first part of this lecture on threads and introduction to concurrency. In the second half, we'll be looking at the actual implementation of threads and the thread API.